equal to 0 and f of r naught equal to 0, and it is the unique falling 0 in our case. Alright, towards the end, I will show this example again. This is an application. This model is coming from ecological systems. We can apply our results to this particular model. In that model, in the reaction term, K and M are some positive parameters. If you compare our model with this one, here mu s is going to be square root of s in this case. Alright, before I state my result, I'm going to talk about some eigenvalue problems here. It's an important question to answer whether we have a principal eigenvalue for that problem. That is the linearized problem associated to our model. Okay, because I'm talking about the case f of 0 equal to 0. This principal eigenvalue plays an important role in that case. So we need to answer that question. Let's come to that question in a second. If you look at this particular eigenvalue problem, for a fixed kappa, the principal eigenvalue b kappa exists, and the corresponding eigenfunction is positive. And what's further known is that these two mathematicians, Mauricio Rivas and Steve Robinson, they proved that the principal eigen curve is a strictly decreasing concave function, like in the figure, which passes through the origin, which is bounded above by BD. BD is the principal eigenvalue of the Dirichlet problem. Okay, they established that concavity of the curve. All right, now we are all set to answer the question. The principal eigenvalue for that linearized problem exists if you assume a condition like this, condition like H1. What the H1 tells you is that there exists kappa naught such that between kappa naught and 0, the curve mu inverse minus kappa lies below the principal eigen curve, and it lies above the principal eigen curve between minus infinity and kappa naught. The principal eigen curve is in blue. Okay. So if that is the case, it is not hard to see that A1 mu, if I take that height, the intersection point, the corresponding height, A1 mu, that's going to be the principal eigenvalue for that linearized problem, because I can trace this A1 mu back to the lambda kappa axis. This is going to be minus mu A1 mu. For that minus mu A1 mu, the principal eigenvalue is also going to be that point, because it's on the principal eigen curve. So that proves you that the principal eigenvalue for that problem exists. So we are good to go. Alright, another eigenvalue problem. What are eigenvalue problems today? So if you, for a fixed lambda, if you look at this particular eigenvalue problem, sigma lambda, the principal eigenvalue sigma lambda exists for this problem, and we can take the corresponding function to be a positive function. And what's further known is that we can prove that if you choose your lambda less than A1 mu, we can show that sigma lambda is greater than 0. And if your lambda is bigger than A1 mu, sigma lambda is less than 0. And most importantly, as lambda approaches to A1 mu, your sigma lambda approaches to 0. Okay? Alright, here is our first results. Existence, non-existence, and uniqueness results. We were able to establish this exact bifurcation diagram, assuming that f double prime is negative on 0, r naught. Remember, r naught is our unique falling 0. What we proved was that there is a unique positive solution beyond A1 mu for lambda bigger than A1 mu. No positive solutions for lambda less than A1 mu. And the subnorm of the positive solution approaches to 0 as lambda approaches to A1 mu from the positive side. And the subnorm approaches to R naught as lambda approaches to infinity. Okay. Right. I'm going to give you an outline of the proof of that theorem. Due to the time constraint, I will only be showing that there is a solution which is branching down to 0. For that, I'm going to be using method of sub and supersolution. Here are the definition of sub and supersolution. A function psi satisfying first two inequalities is called subsolution. And function z satisfying the second two inequalities is called supersolution. Here is an important lemma that we'll be using. If you have subsolution psi and the supersolution z, so that the supersolution is bigger than or equal to the subsolution, the conclusion is that there is a solution between subsolution and the supersolution. Alright, to show that there is a positive solution which is branching down to 0, what I'm going to do is I'm going to construct a small subsolution and a small supersolution so that the subnorm of the supersolution goes to 0 as lambda approaches to 1 mu. Okay? That way, the solution living in between sub and supersolution, the subnorm of that solution will go to 0. Okay? Alright, to achieve that, here is, I'm going to try this function psi, m lambda theta lambda as my subsolution. Theta lambda is the eigenfunction of this eigenvalue problem that I showed you earlier. Notice that I'm going to get the existence beyond a1 mu, beyond the principal eigenvalue. In that case, sigma lambda is negative. Okay. Alright, so to show that it is going to be a subsolution, I need this inequality and the boundary inequality. To show this inequality, I'll be done if I can show this. Okay, this negative Laplacian psi is exactly this expression that needs to be less than or equal to that. To show that, I'm going to treat this m lambda theta lambda as s. If you view it as s, and if you define this new function h of s, using the fact that f of 0 is equal to 0 and f prime of 0 is equal to 1, we can see that h of 0 equal to 0, h prime of 0 is equal to sigma lambda. But sigma lambda is negative. So that means if you choose your s small, h of s is going to be less than or equal to 0. What does that tell you? That tells you that if you choose your m lambda small, that quantity is less than or equal to 0. So we have the inequality in the right direction for psi to be a subsolution. And also the boundary inequality is clear because we have the same linear Robin type boundary condition for this eigenvalue problem. So that means if you choose your m lambda small, this is going to be subsolution for our problem. And here is the construction of the supersolution. Since we assume that f double prime is negative, there exists a star positive. So that if double prime is less than or equal to minus a star for small s, we consider if double prime locally there. And then I'm going to try that function is the delta lambda theta lambda. Delta lambda is defined by that expression there. There, notice that sigma lambda is negative, so it's a positive quantity actually. And sigma lambda goes to 0 as lambda goes to a1 mu. So that means delta lambda goes to 0 as lambda goes to a1 mu. Okay, so the subnorm of the supersolution will go to 0 because we have delta lambda in front. Well, now if you consider that difference, we need to show that that difference is greater than or equal to 0. For that, by Taylor series expansion, we can see that f of c is equal to that expression right there. And we can use the fact that f of 0 equal to 0 and f prime of 0 equal to 1 to get the expression over there. And then we can compute that difference, negative Laplacian z minus lambda f of c. That difference is going to be here, this expression given by this expression. Now we can replace that f double prime zeta is something between 0 and z, by a star because of that inequality to get a small quantity over there. Now by the choice of delta lambda, that expression, the last expression is going to be 0. So that gives you the inequality in the right direction for z to be a supersolution. What do we have now? We have a supersolution. Of course, the boundary inequality is clear in this case also because we take the same eigenfunction theta lambda. It has the same linear type boundary condition as we have in our model. That tells you that C is a supersolution, so that the subnorm of the supersolution goes to 0. So the solution living between psi and z, the subnorm of that solution will also go to 0 as lambda approaches k1 mu from the positive side. Alright, here is the multiplicity results, conditions that I'm going to assume for the multiplicity result. I'm going to assume that there exists a greater than 0, b in that particular interval. Remember, R0 is the falling 0. Cn is defined by that expression over there. And V mu b is the unique positive solution to this problem. And further, I'm assuming that this quantity is greater than the quantity in the right hand side. Here, f star is the maximal function. And V mu b is defined by that quantity. Mu evaluated at that particular number, there R is the largest inscribed ball in your domain. Okay. Alright, further we assume that H3, there exists R between 0 and B, R2 between those two numbers, with F is non-decreasing on the interval R1, R2. Here is a shape of the function that we would expect in this case. Finally, we assume that our principal eigenvalue is less than this particular number because we are establishing our multiplicity result to the right of the bifurcation point. Alright. here is some multiplicity result. If you assume the condition H1 through H4 hold, then for lambda in this particular